Okay, lesson 49, circular motion practice. Please turn to that. It's on page 14 of your packet. And here we go. Let's just churn through this and call it a day. What term means the number of circles made each second? That is going to be frequency. Number 2, the time it takes to make a full circle, make a full rotation, is going to be period. Those are the two biggest terms that you need to know for this unit. And it's oftentimes confusing. I have to think twice to make sure that I say it right. Distance around a circle, as you know from math class, circumference. Number 4, the force that keeps an object moving in a circle, that is the centripetal force. Number 5, the term that means a line perpendicular to the radius, just touching the circle at one point. Again, from your math class, I hope you remember this, tangent. Today's grades. We're not going to have any grades today. Next quiz, lesson 54. Today's 49, so it looks like next week. Does anybody have any questions about any homework that we've done so far? Any of the review sheets or yesterday's paper? Matthew's in the house. Type it in the chat room if you have any questions about yesterday's homework. Okay, today's purpose. I will practice what I learned in the video during the previous lesson. I will practice the concepts of frequency, period, velocity, and centripetal force. Relevance, lots of things move in circular paths. We have carnival rides, drill bits, fan blades, car wheels, etc. Success, you'll be able to measure how fast something is going in a circle in 3 different ways. So just like we can measure velocity in miles per hour and meters per second and centimeters per year or something like that, we can measure the speed of something in different units, and also whether it be degrees per second going around or how many miles per hour going around. There's different ways of doing it in that regards as well. Okay, notes. Let me try to shrink up the pictures here a little bit. There we go. Period. This is how long it takes a motion before it repeats. Oh, I wasn't going to do it that way. I was going to do it with the typing. Let's try it with the typing. How long it takes before it repeats. So it goes around the circle once and it gets to the top of the circle and then it repeats. It goes round and down and then back up to the top of the circle and then round and around the top of the circle. Okay, it repeats. This is measured in seconds. The faster the object circles around, the smaller the period will be. The faster it spins, the smaller amount of seconds it takes to get around to the top again. That makes sense. The variable for period is a capital T. If an object is twirling around and it makes a complete circle in 8 seconds, we say the period is 8 seconds. If it twirled faster and faster, the object takes less time to make a full circle and the period will get smaller. The period will always be reduced, or may be reduced to 4 seconds and then down to 2 seconds and a whole lot less. Number 3, frequency. This is how many repeated circles it makes in a second. The faster the object goes around, the higher the frequency. The variable for frequency is a small letter f. The unit for frequency is the number of cycles per second. This is abbreviation cycles over seconds. This is also abbreviated as hertz. It's a capitalized letter H because it's named after some researcher person. And it's even more abbreviated as capital HZ. You may have seen that on some appliances like radios and perhaps your microwave or your computer. Its speed of computing power is sometimes referred in megahertz. Mega meaning million. Okay, so if the object repeats a circle 5 times in a second, then the frequency is 5 hertz. If it does a full circle and a half in 1 second, then the frequency is 1.5 hertz. Number 5, if a twirling object takes 2 seconds to make a full circle, then it takes a half a circle per second. So looking at, hang on a second, let me get my colors going. Okay, right over here, we have 2 seconds to go all the way around. So it makes sense that if that's 2 seconds, in 1 second, it's only going to go half the way around. Okay, so in one case, we have 1 full circle. 1 full circle there. In the other case, we have 1 full second. So they both have different terms that refer to them. One is for a full second, one is for a full circle. Okay, so let's get these terms down. Number 6, in the statement above, the 2 seconds would be considered the period. That's the time for 1 circle. The half is the frequency. That's how much of a circle you make in 1 full second. Period is a full circle. Frequency is a full second. 1 second. Okay, number 7. Let's suppose a twirling object takes 3 seconds to make 1 full circle. A twirling object, let's say a merry-go-round. One of those little merry-go-rounds you might see at the grocery store where you put in the quarter, you put your little kid in on the seat and just goes around like, 3 feet. It doesn't go very big. It takes 3 seconds to make 1 full circle. Then it takes a third of a circle per second for 1 second then. So in this statement, the 3 would be considered the period. Period is the time for 1 full circle. The 1/3 is going to be the frequency. That's for 1 second. Remember, period is 1 circle. Frequency is how much in 1 second. So here we have a diagram. It goes all the way around in 3 seconds. So that means that in 1 second, it just gets a third of the way. So once again, this is the period. This is the frequency. Frequency is how much you go around in a second. Period is how many seconds to do 1 full round. Okay, so number 9, we have this diagram here to go with number 9 and 10. If a twirling object takes 4 seconds to make 1 circle, then it takes 1/4 of a circle per second. So here it goes all the way around. Goes all the way around 4 seconds to get all the way there. So that means that in 1 second, it just gets that far. So the 4 would be the period. How many seconds to take 1 full circle? The 1/4 is the frequency. How far does it get in 1 second? Okay, we've done the same kind of a thing now over and over and over for 2 seconds, 3 seconds, and 4 seconds. Let's see what the pattern is. You should probably end up seeing the pattern already, right? It's kind of obvious. Number 11, from these examples, we can see that there is a simple relationship between period and frequency. The period is the reciprocal of the frequency. 4 1/4, 3 1/3, 2 1/2. So there's our equation right there. F equals 1 over T. I could also write that then. T is equal to 1 over F. By the way, this F here should be a little f. Capital F is force, little f is frequency. They're reciprocals of each other. So number 12, a spinning carnival ride has a period of 5 seconds. What is the frequency? The 5 seconds here, that is the period. We are looking for the F. So the equation F is equal to 1 over T. Oh, that P should be a T. Oopsie daisy. So that's 1 over 5. Divide that out and you get 0.2. Number 13, a spinning CD may have a period as small as 0.005 seconds. What is the frequency? Okay, period of this. So that is time, capital T. We are again looking for the F. (200 hertz). Number 14, a merry-go-round has a frequency of 0.13 hertz. What's the period? So it has a frequency. This is the F. We are looking for the T. Oh, I forget what the answer is. It's something like 69. Let me pull up my calculator here and find out what that is. 1 divided by 0.13 equals 7.69. Let's call it 7.69 hertz. So that means that in 1 second, it can go around 7.69 times. Oh man, I got caught in a pattern and I didn't get myself out of it in time. Do you see what I did wrong? Check it out. I'm going to give 17 brownie points to the person who could show me what I did wrong. Anybody? The frequency F is 0.13. And I put that in for the T at the bottom. Oh, that's just wrong. That's just, oh, wrong. I had my brain in cruise control. Oh, let's get purple. Okay, so we have F equals 1 over T. Let's do it correctly this time. This frequency, 0.13. What is the period? So the T is what we're looking for. That stays a letter. Okay, so how do we get this T by itself? How do we get all the other numbers on the other side? Well, we make it a proportion and we can switch the diagonals. So we get T is equal to 1 over 0.13. It turns out to be the same number, doesn't it? Huh. I guess I need some more caffeine. They're reciprocals of each other, the period and the frequency. Number 15, a drill goes around with a frequency of 100, so that's the F. What is the time to go around once? That's the period, capital T. So put in our numbers that way. Flippity flop the diagonals. And we get 0.01. Now, what does it mean here to have a frequency of 100? Frequency of 100 hertz. What does that mean? It means that the drill bit spins 100 times every second. Questions so far? Type it into the chat room if you have any questions. What does it mean that the drill has a period of 0.01 seconds? One spin takes 0.01 seconds to complete. Mathematically, what do we call this reciprocal relationship? And we've had this before. It's an inverse relationship. When one gets bigger, the other one gets smaller. If it takes more and more time to go around once, in other words, the period gets bigger and bigger, that means the frequency gets smaller and smaller. If the period gets bigger and bigger, what happens to frequency? Smaller. Okay, so we have learned about measuring the speed of something spinning by either the period or the frequency. Here's another way of doing it now. A third way of measuring how fast something is going around in a revolution is its velocity. Let's do typing this time. Earlier this year, we learned the definition of velocity given by the equation. Let's see here, delta V. How should I do this delta V? Delta X, I should say. Delta X divided by T. That's the equation that we had oh so long ago. If we are to measure the velocity that something's going in a circle, it would make sense that we measure how much time it takes to go around the circle once and how far it moves as it goes around in that one circle. So the delta X is how far it moves in a circle, one circle. The T is how much time it takes to do that one circle. So there we have, come on, there we go. Here we have that same fraction up above here, just in word format. Number 22, the distance the object moves in one circle is known as the circumference. And the equation is 2 pi r. We can put that on the top of the fraction. So instead of how far it moves in one circle on the top, I have the equation 2 pi r. Now let's look at the bottom part, how much time it takes to go around in one circle. The time on the bottom is the time for one revolution. We defined that at the beginning of the lesson to be the period T. So we can put this at the bottom. We can put the capital T before we had a little tiny t. The little tiny t is the time for anything to happen. In this case, moving delta X. But now we have a special kind of a time, the time for one circle. So we put the capital T in for that. It doesn't really make a difference if you're worried about it. I just want you to know why I write things in certain ways. Okay, so here we have the equation for the velocity of something moving around in a circle. the distance around the circle, and the time for one circle. Number 24, a child is sitting at the edge of a merry-go-round. The ride has a radius of 3 meters. The ride takes 4 seconds to go around once. What is the velocity? Okay, so V is equal to 2 pi r divided by t. The r, the radius, is 3 meters. And the time is 4 seconds. So I multiply that out. Let's see here. That's going to be 2 times pi times 3 divided by 4 equals 4.71. Number 25, the ride keeps going around at the same rate of 4 seconds per turn, but the child moves towards the center of the ride, so the child is now only 1 meter from the center. What's the velocity now? So think, as you go closer and closer to the center of the merry-go-round, do you spin faster or slower? Think about it for a second. Make a little jot here. Put F for faster, S for slower. Make a commitment. Think to yourself, what would it be? And let's see if you're right or not. The R is not 3 anymore. The R is 1. But the time to go around once is still going to be 4 seconds. It doesn't matter what part of the merry-go-round you are on. It's still all spinning the same number of revolutions every second. Okay. Typing this out into our calculator, 2 times pi divided by 4. I get 1.57. So it's slower. And I hope you recognize that. Maybe. It's been a long time, perhaps, since you've been on a merry-go-round. Number 26. A parent is pushing their child on a merry-go-round by grabbing onto the rail and running. The parent can run at 5 meters per second. The merry-go-round has a radius of 3. How long will it take for the ride to make one full turn? Okay, so this here is our velocity. It says very clearly radius of 3 meters, so that's a r. How long? It's asking us to find out the t. So making our equation, let's see here, the V is 5, the R is 3, we're looking for the T. Flip-flop the diagonals. Pull out the calculator. I get 3.7. 3.7 seconds to go all the way around. On your own right now, try number 27. It's very similar to what we just did. A spaceship is moving at 80 meters per second. Circle the 80. What variable is that going to equal? It steers its engines so that it goes around and around the space station once every 120 seconds. Circle the 120. What variable is that equal to? What is the radius of its circular path? Circle the question mark. What variable are we looking for? Okay, so you should have written that the 80 is the V and the 120 is the capital T, and we're looking for the R. Keep on going. Try to do it on your own. So to solve for the r, I would multiply both sides by 120, divide by 2, divide by pi, and I get 1,528 meters. Number 28, if everything else stays the same, what happens to the velocity as the radius doubles and doubles and doubles? Well, looking at this equation up here, as this number here gets bigger and bigger, the v is going to get bigger and bigger. And it's going to get bigger at the same rate. So if you double the r, you're going to double the velocity. V will double and double.